All right, so let me do a couple of problems very quickly. Here's 925A. Why is it impossible for a set of numbers S which has more than one element, includes 0, to be a group under multiplication? I suggest that you show two things here. First of all, you show that 0 must be the identity element. In such a case, if you have such a case, a set of numbers, show that 0 must be the identity element. Then show that 0 cannot be the identity element. All right, now 1 is true no matter whether or not S has more than one element. The second one is true. This is only true. This requires that S is greater than 1. Okay. All right. Now, so you should think about what identity element means. Identity element means that ID times any element is equal to that element. All right. So think about those two conditions and show both of them. That will be sufficient to prove the result. All right, for 928, I think I'm just going to talk through this one. Again, if you want to show something as a group, you just need to go through the four properties. First of all, closure. You can just say that by definition, the AB composed CD is a coordinate pair, so H is closed under circle. If you want to show associative, you can just write down what the associative law is and show that it works. Write down what the associative law would imply and show that it works. The basic idea is that the associative law works for each coordinate in the pair, so it works for the coordinate pair. Identity, you can write that down. Inverse, you can write that down. So that shouldn't be more than half a page. All right, just list the properties one by one, work through them very quickly. Okay, so let me say a little bit about 9 to 12. Here we have a definition of the product of groups. And we want to show that the product of groups is in fact a group. So what does this definition say? It defines the element of a product of groups, which is a pair of group elements. The first element in the pair is from the first group. Second element of the pair is from the second group. And it also defines the operation. So you need to show the four things again. You can just say that like this, closure. You can say by def 9 to 10 if G1 H1 and G2 H2 are elements of G cross H, then G1 H1 circle G2 H2 is also an element of G cross H. You can see right here, this is what the definition says. If you have two ordered pairs, then the result is also an ordered pair. So there's your closure. Then you have associative property. Write down what that means. If you take G1 H1, G1 comma H1, just write down what it means. Circle G2 H2, circle G3 H3. Okay. Now what's that equal to? It's equal to G1 G2 H1 H2 circle G3 H3. and that's equal to G1, G2, G3, H1, H2, H3, and that's equal to, now I can use the associative property on the individual groups, so that's equal to G1, G2, G3, H1, H2, H3, and this is by associative property of G and H. Okay. And that's equal to G1, H1, composed, G1, G2, G3, H2, H3. And that's equal to G1, H1, composed, G2, H2, composed, G3, H3. Okay, all right. That's a little bit more writing, but it's still only 4 lines. All right, then identity should be very straightforward. Just exhibit an element such that the product gives you the original result. So you could say something like this: let, if you want some notation, you can say let EG be the identity. Well, let's just say it this way. Let IDG and IDH be the identities of G and H. Then, so you need some identity element, and then you say comma, composed with GH equals GH composed with whatever element you're going to do is equal to GH. That's enough to show identity. And then you do something similar for inverse. You would say let G inverse and H inverse be the inverses of G and H, and then write down a similar statement to get the inverse. Okay, for exercise 9.2.15a, you just want to see whether these group Cayley tables correspond to groups. And don't waste your time writing down a lot of stuff if it's not a group. If it's not a group, then just go ahead and say it's not a group and tell why, and then move on. For example, for part A here, first of all, you can check if it has identity. Now notice that you can assume the associative property, so you don't need to check that one. Well, and they all have closure, so you're not even going to have to check that. It's clear they all have closure because all of the letters inside the table are letters on the margins. So let's check identity. In this case, identity is A, because A circle X equals X circle A is equal to X for all elements, and you can write it that way. Then you also have to check inverse. So let's see. It's clear that A is the inverse of A because A times A is equal to A. Looks like B is the inverse of B because B times B equals A. So then it looks like C is the inverse of C. Now what about D? Here you have D times B equals A, but you don't have B times D equals A. So you can simply say D has no inverse because D circle B equals A, but B circle D is not equal to A. All right? So in fact, you could just write that single statement and move on. Or actually, you would need to mention that A is the identity. So you could say for part A that element A is the identity because A circle X equals X for every X in G. But D has no inverse because D circle B equals A, but B circle D is not equal to A. Okay, so you can just give the statement and the reason. Shouldn't take too much writing. All right, for 9.2.16, You don't have to give reasons for filling in the blanks. You don't need to write down the reasons, that is, but of course you should have a reason. Okay. For instance, you can pretty much tell what this element's going to be. You don't need to give a reason, just put it in and then make the whole table work. Just make sure you've got your identity and inverse. You can assume associativity. Okay, that's it for the problems that I'm going to review in 9.2. Make another video for 9.3. Alright, let's move on to exercise 9.2.12. Show that the product of two groups is a group. Now the product of two groups, G and H, is a set of pairs. The first element in the pair is from G, the second element of the pair is from H. And the group operation on this set of pairs is defined as follows. G1H1, circle G2H2 equals G1G2 and H1H2, where this is the group operation on G and this is the group operation on H. Now if you think about it, this is really a generalization of what we just saw in 9.2.8. 9.2.8 is also a set of coordinate pairs. In this case, both elements in the pair are from the integers. In this case, the group operations are both plus, but you can see that this specification is exactly the same as the specification that we saw in 9.2.12, except we have the operation plus instead of the general group operation. So look at this here and compare this one here, right? Group operation one, group operation, group element one, group element one are operated together. The element of group 2, element of group 2 are operated together. Right? So we're really going to follow pretty much the same procedure. I gave some blanks here for you to fill in. So you fill in this blank here and here. I'm not sure how much I need to talk through this, but each time you make a step, you should give a reason. Now, because you're space limited, you may want to put more than one step on one line. For instance, this step here and this step you could put on one line, and you could put the next two steps on one line. But you can see that pretty much the justifications you're using are the definition of the group operation and the associativity of G and H. So that's the strategy, is to prove that a product of groups is a group. You break it down to the properties of the individual groups that form the product. All right. So here I have these blanks here, so you can see several blanks. If you want to fill in the, if you want to do it yourself, that's fine. If you want to go do this fill in the blanks formula, that's fine too. All right. But you do have to show the associative relation. So here I've gone all the way down in this argument and ended up with the reassociation of these three group elements, right? I've taken three arbitrary group elements, the first one composed with a composition of the second two, and end up with a composition of the first two composed with the third one. All right, now, so that's associative. Now, of course, you want to do identity, and then to use identity, I suggest you use this kind of notation. Let EG and EH denote the identities of G and H respectively, because you don't know what they are. You could use 1G, 1H, or you could use some other terminology, but you're going to need some kind of terminology that indicates what the identity of G is and the identity of H is. And remember what you have to show, that any element of the product group composed with the identity will be equal to that same element of the product group. And the identity composed with any element of the product group is that same element of the product group. So you have to decide what this identity is going to be You have to fill in those blanks and figure out what the identity element is going to be. I think it shouldn't be too tough to figure that out. Now the proof of inverse is very similar. You're going to define the inverse of a product element in terms of the inverses of the individual components of the product. So you can say, you'll take something like GH composed with something, and then you'll get what you'll have to get here is your identity element, and then you'll have to do the same thing. You'll have to do the something composed with GH also gives you the identity element. So hopefully that gives you a good outline on how to do this problem. All right, moving forward to 9.2.16. This is just fill in the Cayley table. It mentions in the book that you don't need to prove associativity, but using the properties of identity and inverse, then you can fill in these tables uniquely. Just fill in the blanks, you don't need to give reasons. All right, so that completes the video for 9.2, and you can move on to the next video if you like.